Hey science enthusiasts, ever wondered how charged particles move within electromagnetic fields? Buckle up, because today we're diving deep into plasma physics and the motion of charged particles. First off, let's talk about how plasmas like to disperse. Without any restraint, these energetic particles would just fly off in all directions. Enter magnetic fields. These fields, thanks to the Lorentz force, act like invisible reins, keeping those particles in check. Now the key player here is the Lorentz force equation dp dt equals sine q E plus vxb. What does this mean? It means the momentum of a particle with charge q and velocity v changes in the presence of electric field E and magnetic field B. In a constant electric field, positively charged particles accelerate along the field, while negatively charged particles move the opposite way. Pretty straightforward, right? But what happens in a uniform magnetic field? Well, the Lorentz force makes particles move in a circular trajectory, forming a helical path. This rotation frequency is known as the cyclotron frequency. The radius of this circle is called the Larmor radius. Let's compute it. For an electron with 1 keV energy in a 1 Tesla field, the Larmor radius is about 1.3 x 10 circumflex 3 meters. Cool, right? But wait, there's more. This circular motion creates a magnetic moment opposing the external magnetic field, a phenomenon known as the diamagnetic effect. Now let's talk about drifts. In a uniform magnetic field, the guiding center can drift if a non-magnetic force acts on it. For instance, a sudden collision changes the particle's velocity, causing a perpendicular shift. Or, if an electric field is applied, you get the E cross B drift, moving perpendicular to both fields. And in non-uniform magnetic fields, the cyclotron orbit shortens and lengthens periodically, leading to a net drift. This drift depends on the magnetic field gradient and curvature. Some particles get trapped in strong magnetic fields, bouncing back and forth between mirror points, crucial for magnetic confinement fusion reactors. So, to recap, we've explored the Lorentz force, helical motion, Larmor radius, guiding center drifts, and particle trapping. These are the building blocks of plasma dynamics. If you enjoyed this deep dive into plasma physics, hit that like button, share, and subscribe to the channel for more science content. Stay curious and stay scientific. In this extended section, we'll delve into the applications of plasma physics in modern technology. From fusion reactors to space propulsion, plasma physics plays a crucial role in advancing our technological frontiers. Stay tuned as we explore these exciting applications. First up, fusion reactors. Imagine harnessing the same energy that powers the sun right here on Earth. Fusion reactors aim to do just that by fusing hydrogen isotopes to release massive amounts of energy. The challenge lies in containing the ultra-hot plasma, reaching temperatures of millions of degrees. That's where magnetic confinement comes into play. Using devices like tokamaks and stellarators, scientists create powerful magnetic fields to keep the plasma stable and contained, making fusion energy a tantalizing possibility for a sustainable future. Next, let's venture into space propulsion. Traditional rockets rely on chemical reactions for thrust, but plasma propulsion systems, such as ion thrusters, offer a more efficient alternative. By ionizing a propellant and accelerating it using electric and magnetic fields, these thrusters achieve higher speeds and greater efficiency, making long-duration space missions more feasible. This technology is already in use for satellite positioning and interplanetary missions, pushing the boundaries of space exploration. But that's not all. Plasma physics also finds applications in materials processing, such as plasma etching and semiconductor manufacturing. By using plasma to precisely remove material from surfaces, manufacturers can create intricate microchips and electronic components, driving the miniaturization of technology. And let's not forget medical applications. Plasma can be used for sterilization, wound healing, and even cancer treatment. Cold plasma jets can kill bacteria and promote tissue regeneration, offering innovative solutions in healthcare. From energy to space exploration, manufacturing to medicine, plasma physics is at the heart of groundbreaking advancements. It's an exciting time for science and technology, and we're just scratching the surface of what's possible. If this journey into the world of plasma physics has sparked your curiosity, don't forget to hit that like button, share this video, and subscribe to our channel for more fascinating science content. In this final chapter, we'll explore the future of plasma physics and its potential impact on various fields. From sustainable energy solutions to advanced medical treatments, the possibilities are endless. Stay tuned as we dive into the cutting-edge research and innovations that are shaping the future of plasma technology. Imagine a world where fusion reactors provide virtually limitless clean energy, eliminating our dependence on fossil fuels and reducing greenhouse gas emissions. Scientists are making strides in achieving this dream, with experimental reactors like ITER and advancements in magnetic confinement techniques bringing us closer to a sustainable energy future. In the realm of healthcare, plasma technology holds the promise of revolutionary treatments. Researchers are developing plasma-based cancer therapies that target and destroy tumor cells without harming surrounding healthy tissue. Additionally, plasma sterilization methods are becoming more effective and accessible, offering new ways to combat antibiotic-resistant bacteria and improve wound healing. The potential of plasma physics extends beyond Earth, too. As we look to the stars, plasma propulsion systems could enable faster and more efficient space travel, making interplanetary missions a reality for future generations. Imagine humans exploring Mars and beyond, with plasma technology paving the way for these incredible journeys. But the impact of plasma physics isn't limited to energy, healthcare, and space. In materials science, plasma processes are enabling the creation of new, advanced materials with unique properties, from superconductors to innovative nanomaterials. These breakthroughs have the potential to revolutionize industries ranging from electronics to construction. The future of plasma physics is bright, and the innovations on the horizon are set to transform our world in ways we can only begin to imagine. If you enjoyed this video, don't forget to like, share, and subscribe for more exciting science content. Stay curious and stay scientific. Imagine a world where we can harness the power of the stars right here on Earth. This is the dream of fusion energy, and magnetic mirrors are a key player in making it a reality. But what are magnetic mirrors? Simply put, they are regions of strong magnetic fields that can reflect charged particles like tiny magnets bouncing off a wall. This effect is crucial for confining plasma, the superheated gas that fuels fusion reactions. To understand magnetic mirrors, we need to understand how charged particles dance in a magnetic field. This dance is a fundamental aspect of plasma physics and space science. Imagine a tiny charged particle like an electron zipping through space at incredible speeds. When it encounters a magnetic field, it experiences a force perpendicular to both its velocity and the magnetic field direction, known as the Lorentz force. This force makes the particle spiral around the magnetic field lines like a bead on a twisted wire, creating a helical path. The angle between the particle's velocity and the magnetic field line is called the pitch angle, a crucial parameter in understanding particle motion. A small pitch angle means the particle is moving mostly along the field line, while a large pitch angle means it's spiraling tightly around it, affecting its trajectory significantly. Now imagine a magnetic field that gets stronger at both ends, like a bottleneck. This is the essence of a magnetic mirror. As a charged particle travels towards the stronger field region, it experiences a force that pushes it back towards the weaker field. This is the magnetic mirror effect in action. The particle's pitch angle determines whether it escapes the mirror or gets trapped. If the pitch angle is small enough, the particle will be reflected back and forth between the mirror points, effectively confined within the magnetic bottle. However, if the pitch angle is too large, the particle will escape the mirror. Section 4. Plasma confinement and key phenomena. In the world of plasma physics, confinement is key to sustaining reactions. We need to keep the superheated plasma contained and away from the walls of the reactor, where it would cool down and halt the fusion reaction, making the process inefficient. Magnetic mirrors offer a promising approach to achieve this, using magnetic fields to confine plasma. Two important phenomena govern the motion of charged particles in magnetic mirrors: cyclotron frequency and curvature drift, both crucial for effective confinement. The cyclotron frequency describes how fast a charged particle spirals around a magnetic field line, a fundamental aspect of plasma behavior. Curvature drift, on the other hand, arises from the curved nature of the magnetic field lines in a mirror, causing particles to drift slowly perpendicular to the field, impacting overall stability. Section 5. Applications of magnetic mirrors. Magnetic mirrors have found applications beyond fusion energy research. They are used in astrophysics to study the behavior of charged particles in space plasmas, such as those found in the Earth's magnetosphere and the solar wind. Additionally, magnetic mirrors are employed in particle accelerators, where they help to confine and accelerate beams of charged particles for various research purposes. Section 6, Challenges and Future Directions. While promising, magnetic mirrors face certain challenges. One major hurdle is the loss of particles through the ends of the mirror, known as end losses. Researchers are actively exploring ways to minimize these losses and improve confinement efficiency. Another challenge is maintaining the stability of the plasma within the mirror. Plasma instabilities can cause the plasma to leak out of the confinement region, disrupting the fusion process. Scientists are developing advanced control systems and innovative mirror designs to mitigate these instabilities. Section 7. Conclusion: Mirrors reflecting a bright future. Magnetic mirrors offer a fascinating window into the world of plasma physics and hold immense potential for unlocking the power of fusion energy. By understanding the fundamental principles of charged particle motion in magnetic fields, we can design and optimize these mirrors for a variety of applications. As research and development continue, magnetic mirrors promise to reflect a bright future for both fundamental scientific discoveries and practical technological advancements. In this final chapter, we will explore the future possibilities of magnetic mirrors in fusion energy, a field that holds immense promise for sustainable power. As technology advances, the potential for magnetic mirrors to revolutionize energy production becomes more tangible, bringing us closer to a new era of clean energy. Researchers are optimistic that with continued innovation, we can overcome current challenges and unlock the full potential of fusion energy, making it a viable solution for the future. The journey of magnetic mirrors is just beginning, and the future looks incredibly promising, filled with opportunities for groundbreaking discoveries. Imagine a world where clean, limitless energy is no longer a dream but a reality, transforming the way we live and interact with our environment. Magnetic mirrors could be the key to unlocking this future, providing not only sustainable energy but also advancing our understanding of the universe and its fundamental forces. As we continue to push the boundaries of science and engineering, magnetic mirrors stand as a beacon of hope, guiding us toward a brighter, more sustainable future for all. The road ahead is filled with challenges, but with perseverance and ingenuity, we can harness the power of magnetic mirrors to transform our world and secure a better tomorrow. The journey is just beginning, and together we can reflect a future that is bright, sustainable, and full of possibilities, driven by the power of innovation. Thank you for joining us on this journey through the fascinating world of magnetic mirrors, where science meets the future. Stay tuned for more exciting developments in the field of plasma physics and fusion energy, as we continue to explore new frontiers. The future is bright, and it's just around the corner, waiting to be discovered. Our universe is awash in plasma. Plasmas are not some exotic form of matter. They are more common than the familiar states of solid, liquid, and gas. A plasma is simply a gas where the atoms have been stripped of some or all of their electrons, leaving behind a mixture of charged particles, ions, and electrons. This sea of charged particles is profoundly influenced by magnetic fields. One of the most fascinating phenomena in plasma physics is cyclotron resonance. Imagine a lone electron, a tiny charged particle caught in a magnetic field. The magnetic field forces the electron into a circular dance, a perpetual orbit around the magnetic field lines. This dance, this orbit, is the key to understanding cyclotron resonance. Now picture bathing this electron and its magnetic field in electromagnetic waves, light, radio waves, or even X-rays. These waves carry oscillating electric and magnetic fields. If the frequency of the incoming wave matches the electron's natural orbital frequency, something amazing happens. The electron absorbs energy from the wave, much like a child on a swing gains momentum from well-timed pushes. This is cyclotron resonance, a symphony of motion and energy transfer between charged particles, magnetic fields, and electromagnetic waves. Every orbiting object has a natural frequency, a rhythm that dictates its motion. For planets around a star, it's the orbital period. For electrons in a magnetic field, it's the cyclotron frequency. This frequency is determined by the charge of the electron, its mass, and the strength of the magnetic field. Think of a lightweight electron in a strong magnetic field. It will whirl around the magnetic field lines at a rapid pace, just like a lightweight on a fast merry-go-round. A heavier particle or a weaker magnetic field would lead to a more leisurely spin. The cyclotron frequency is the key to unlocking cyclotron resonance. When the frequency of an incoming electromagnetic wave matches this natural frequency, the electron is perfectly timed to absorb energy from the wave. It's like pushing a swing at just the right moment to send it soaring higher. Imagine the ripples spreading out from a pebble dropped in a pond. These ripples, these waves, are disturbances propagating through the water. Electromagnetic waves, like light and radio waves, are disturbances propagating through the electromagnetic field. When these waves travel through a plasma, they don't always travel in a straight line at a constant speed. Their speed and direction can change depending on the properties of the plasma and the frequency of the wave. This relationship between the wave's frequency and its speed is described by what physicists call a dispersion relation. Dispersion relations are like the traffic laws of the plasma world, governing how waves propagate through this sea of charged particles. They tell us how the wave's energy is distributed and how different frequencies will behave. Imagine pushing that child on the swing again. If you push at any random frequency, sometimes you'll add a little energy, sometimes you'll slow them down. But push at their natural frequency, and you'll see them soar higher and higher. Cyclotron resonance works in a similar way. When the frequency of an electromagnetic wave matches the cyclotron frequency of charged particles in a plasma, resonance occurs. This resonance has profound consequences. The most significant effect is the transfer of energy. The electromagnetic wave surrenders its energy to the particles, boosting them to higher energies. This energy transfer can have a dramatic impact on the plasma's temperature, its density, and even its stability. Section 5. Faraday's Cosmic Waltz. Unveiling the secrets of polarization. Light and all electromagnetic waves are more than just oscillating electric and magnetic fields. They also possess a property called polarization, which describes the direction of the electric field's oscillation. Imagine a wave on a string. You can shake the string up and down, side to side, or at any angle in between. Each of these shaking directions represents a different polarization. When polarized light travels through a magnetized plasma, something remarkable happens. The plane of polarization, the direction of the electric field's oscillation, rotates. This phenomenon, known as Faraday rotation, is a direct consequence of cyclotron resonance. As the wave interacts with the spiraling electrons, it experiences different refractive indices for different polarizations. This difference in refractive indices causes the rotation of the polarization plane. The amount of rotation depends on the magnetic field strength, the plasma density, and the distance the wave travels through the plasma. Section 6. Plasma in action. From fusion reactors to the vast expanse of space, cyclotron resonance and Faraday rotation might seem like esoteric concepts confined to the realm of theoretical physics. However, these phenomena have very real and important applications, from unlocking the power of fusion energy to probing the secrets of distant stars. In fusion reactors like ITER, scientists are attempting to recreate the conditions found at the heart of the sun. Extreme temperatures and pressures where hydrogen atoms fuse to form helium, releasing tremendous energy in the process. Cyclotron resonance is used to heat the plasma in these reactors to millions of degrees, bringing them closer to the conditions necessary for fusion. Meanwhile, astronomers use Faraday rotation as a tool to study the magnetic fields of distant celestial objects. By observing how the polarization of light from distant stars and galaxies is rotated as it travels through interstellar space, astronomers can map the magnetic fields that permeate our galaxy and beyond. Section 7. Test your understanding. Exploring cyclotron resonance. Ready to put your knowledge to the test? Here are a few exercises to deepen your understanding of cyclotron resonance. 1. Calculate the cyclotron frequency. Imagine an electron in a magnetic field of 1 Tesla. Using the formula for cyclotron frequency, calculate how many times per second this electron will orbit the magnetic field line. 2. Ponder the impact of resonance. Consider what happens to the energy of an electron when the frequency of an electromagnetic wave matches its cyclotron frequency. How does this energy transfer affect the plasma? 3. Explore Faraday rotation. Research how astronomers use Faraday rotation to study the magnetic fields of distant stars and galaxies. What can we learn about the universe from this phenomenon? Section 8. Conclusion. Unveiling the mysteries of the plasma universe. Our universe is a plasma universe. From the fiery heart of the sun to the diffuse interstellar medium, plasma is the dominant state of matter. Understanding the behavior of plasmas is crucial to unraveling the secrets of the cosmos. Cyclotron resonance, with its interplay of charged particles, magnetic fields, and electromagnetic waves, is a fundamental phenomenon that governs the behavior of plasmas. By studying this fascinating phenomenon, we gain insights into the dynamics of stars, the evolution of galaxies, and the very fabric of space-time itself. Section 9. Further exploration, delving deeper into plasma physics. The world of plasma physics is rich and complex, offering endless opportunities for exploration. If you're eager to delve deeper into the mysteries of cyclotron resonance and beyond, here are a few avenues for further exploration. Textbooks. Explore introductory plasma physics textbooks, such as Introduction to Plasma Physics and Controlled Fusion by Francis Chen, or Plasma Physics for Astrophysics by Russell Kulsrud. Online resources. Discover a wealth of information on plasma physics through online resources like the NASA Goddard Space Flight Center's Science of the Sun website or the ITER organization's website. Research articles. For a more in-depth exploration, delve into research articles published in journals like Physics of Plasmas or the Astrophysical Journal. Gap 3S. Section 10. The cutting-edge latest advancements in cyclotron resonance research. As we venture further into the 21st century, groundbreaking advancements in cyclotron resonance research continue to reshape our understanding of plasma physics and its applications. One of the most exciting recent developments comes from the realm of laboratory experiments. Researchers at the Princeton Plasma Physics Laboratory have successfully conducted experiments using high-power microwave beams to induce electron-cyclotron resonance heating in plasma. This technique has shown promise in achieving higher plasma temperatures and improved confinement, which are critical for the development of sustainable nuclear fusion reactors. Meanwhile, in the field of space physics, the European Space Agency's cluster mission has provided unprecedented insights into cyclotron resonance phenomena occurring in the Earth's magnetosphere. By analyzing data from multiple satellites, scientists have observed intricate wave-particle interactions that help explain the acceleration of particles in space, contributing to our understanding of space weather and its impact on satellite technology. Moreover, advancements in computational simulations have allowed researchers to model cyclotron resonance with greater precision. These simulations have revealed new aspects of wave-particle interactions, such as the role of nonlinear effects in energy transfer processes. These findings not only deepen our theoretical understanding, but also pave the way for practical applications in fields ranging from astrophysics to communications technology. As we look to the future, the potential of cyclotron resonance research appears boundless. With continuous advancements in experimental techniques, observational tools, and computational models, we are on the brink of unlocking even more secrets of this fascinating phenomenon. Stay tuned as we continue to explore the ever-evolving world of plasma physics and its transformative impact on science and technology. Gap 3S. This concludes our journey through the intricate and captivating world of cyclotron resonance. We hope you found this exploration enlightening and inspiring. Don't forget to like, share, and subscribe for more deep dives into the wonders of physics and beyond. Thank you for watching. Gap 3S, Section 11, Practical Applications in Modern Technology. As we delve deeper into the realm of cyclotron resonance, it's essential to highlight its profound impact on modern technology. The principles of cyclotron resonance are not confined to theoretical research or space phenomena. They have found significant practical applications in various fields, including medical imaging and telecommunications. In the medical field, cyclotron resonance has revolutionized imaging techniques. One of the standout applications is in magnetic resonance imaging, MRI. MRI machines utilize the principles of nuclear magnetic resonance, which is closely related to cyclotron resonance, to produce detailed images of the human body. By manipulating magnetic fields and radio waves, MRI technology can provide non-invasive, high-resolution images of internal organs and tissues. This has become an indispensable tool for diagnosing a wide array of medical conditions, from brain disorders to joint abnormalities. Moving on to telecommunications, cyclotron resonance has played a crucial role in enhancing signal transmission and reception. In satellite communications, the interaction between electromagnetic waves and charged particles in the ionosphere can affect signal propagation. By understanding and harnessing cyclotron resonance phenomena, engineers have developed methods to mitigate signal distortion and improve the reliability of satellite-based communication systems. This has led to more stable and efficient global communication networks, enabling everything from GPS navigation to international broadcasting. Furthermore, cyclotron resonance principles are being explored to develop advanced materials and devices. Researchers are investigating the use of cyclotron resonance to create high-frequency oscillators and amplifiers, which could significantly boost the performance of electronic devices. These advancements hold the potential to revolutionize various industries, from consumer electronics to defense technology. The practical applications of cyclotron resonance highlight its versatility and transformative potential. As we continue to explore and understand this phenomenon, we can expect even more innovative technologies to emerge, shaping the future of medicine, communication, and beyond. Gap 3S. This concludes our journey through the intricate and captivating world of cyclotron resonance. We hope you found this exploration enlightening and inspiring. Don't forget to like, share, and subscribe for more deep dives into the wonders of physics and beyond. Thank you for watching. Gap 3S. Section 12. The future of cyclotron resonance. As we bring our journey through cyclotron resonance to a close, let's take a moment to recap the key points we've explored and consider what the future holds for this fascinating field of study. We began with an introduction to cyclotron resonance, delving into its fundamental principles and the electron-cyclotron frequency. We then navigated through the complexities of dispersion relations and examined the conditions and consequences of cyclotron resonance in various environments. Our journey took us to the intriguing realm of polarization, where we uncovered the secrets behind the behavior of electromagnetic waves and plasma. From fusion reactors to the vast expanse of space, we saw how cyclotron resonance plays a pivotal role in both terrestrial and extraterrestrial settings. We explored its applications in modern technology, including its transformative impact on medical imaging and telecommunications. We also peered into the mysteries of the plasma universe and delved deeper into the field of plasma physics. In our exploration of the latest advancements in cyclotron resonance research, we discovered how scientists are pushing the boundaries of knowledge, uncovering new phenomena, and developing innovative technologies. The practical applications we discussed, from MRI machines to satellite communications, highlight the immense potential of cyclotron resonance to revolutionize various industries. Looking ahead, the future of cyclotron resonance research is brimming with possibilities. As technology continues to advance, we can expect even more groundbreaking discoveries and applications. Researchers are working tirelessly to unlock new insights into the behavior of charged particles and electromagnetic waves, paving the way for novel technologies that could reshape our world. Imagine more precise and efficient medical imaging techniques, more reliable and faster communication networks, and advanced materials with unprecedented properties. The potential for innovation is limitless, and cyclotron resonance stands at the forefront of this exciting frontier. As we conclude this video, we hope you feel inspired by the wonders of cyclotron resonance and the boundless opportunities it offers. Thank you for joining us on this captivating journey. Don't forget to like, share, and subscribe for more deep dives into the wonders of physics and beyond. Until next time, stay curious and keep exploring. If you're passionate about nuclear science, you need to know Dr. Tariq Farooq Nagla. He's the powerhouse behind Egypt's nuclear advancements. Professor Dr. Tariq Farooq Nagla is a leading light in Egypt's nuclear landscape. As a research scientist at the Nuclear Power Plants Authority, his groundbreaking work is driving Egypt's energy future. But his contributions go beyond the lab. Dr. Nagla is inspiring the next generation of scientists through his educational initiatives at El Dabaa Nuclear School and beyond. His dedication to knowledge and mentorship is shaping the minds that will lead us into a brighter, sustainable future. Thank you, Dr. Nagla, for your incredible contributions to nuclear science and education. Here's to a future powered by your vision.